Hi there, welcome back to part 2 of how cameras measure the colors in the world. I'm assuming you've seen part 1, otherwise it is wise to go look for it. And also I will add a link at the back of the video. So what did we learn in part 1? We learned that colors, although they happen in the brain, already exist as precursors in the real world. So-called spectra. What is a spectrum? A spectrum is all the elementary wavelengths of different wavelengths which give a different color impression to the eye, ranging from blue over green, yellow, all the way up to red. And for each of these elementary waves there's an amount of energy which is represented by the height of the spectrum. And in this case, if there are lots of energies in the red waves and a little bit in the green and the blue, you're going to see a reddish, probably an orange kind of color. And we can actually calculate what color you will see. Because in fact, you can also fool the eye by thinking you make any kind of spectrum you can possibly imagine in nature, and that's quite a lot of course, by just adding 3 kind of elementary colors, a red, a green and a blue, because of metamerism. And why is that? Because in the eye there are only 3 kinds of cones which measure. There's not 20 or 40 different kinds which measure all these heights. The eye just measures the sum of the heights in a first band, the short wavelengths, the blues, in a second one and in a third one. So you could actually say this spectrum is approximately equal to just the energies or heights of 3 different lamps. Now, before we can build a camera which measures automatically how high these levels should be for each possible spectrum we can encounter in nature, for example the spectrum of an orange or a lemon, which will have more yellows in it of course, so that our display, or printer for that matter, will give the pixels, the red, green and blue pixels, the right amount. Before we can build a camera which automatically does that for anything in the world, that's almost magic, huh? We have to understand, we need to define what color actually is, so that we can define these values. Now, there were color definitions before, like for example atlases of patches, all kind of differently colored patches, and then you can say this lizard is patch number 14. But now you need some kind of mathematical representation, so that you can, with 3 numbers, define exactly and uniquely all the colors you need. How do we do that? It sounds difficult, but actually it wasn't all that difficult. 2 guys in the beginning of the 20th century had a brilliant insight. They said, look, we knew already, as we saw in the first video, that you can make any color by combining a certain amount of energy or intensity of a blue lamp, a green lamp and a red lamp. You shine it on a patch and then you can make whatever color you want. On the other side, you make variable colors. So you take all these elementary colors, all the different wavelengths, and you take, for example, the wavelength that in the previous one made yellow, and you make this yellow wavelength. And then you measure how intense the viewers should make these 3 lamps. So for example, for 460 nanometers, the blue is blue, you need to give this one intensity 1, this 2 times as much, this 3 times as much. If you make the blue a little bit more greenish, it needs to be 1 to 2 and so on, and you write down all these numbers. Well, then you have a representation of how to make any spectral color in nature, because you know it will look the same, at least to some of your observers. These 2 colors will then not be different, but will both be yellow if you mix it in the correct amount. So you need to reduce the intensity of red a little bit to make this orange a little bit more yellowish. And if you have additive colors, there's a fantastic property. It's just adding photons and fooling the eye So if you know how all the wavelengths will be recreated by amounts here, if you take a spectrum with all the various wavelengths together, so any possible spectrum, you just need to add all these numbers that you had for the energies of elementary colors. And that's it. There's another fantastic property, even more brilliant. You can define these primaries at will. Because again, the eye doesn't care whether this is a certain red laser or another slightly different red. It just counts the effect of the photons. One laser will give a little bit more effect in the eye than the other one, but if it's a factor 2, for example, you can do the division and you can calculate one from the other. So that is very interesting, because then we can make a standard observer. We don't have to remeasure all the experiments of the first guy in the second guy. We can calculate what this guy would have measured in case he would have had the choices of the other experimenter, or even something else, or even something else, or even something else. And that's a very interesting property. How does it actually work? Again, it's not so difficult, just bear with me. Suppose we have Mr. Guild. He has selected this kind of green and this kind of red. So suppose it's a green laser and a red laser, only one elementary wavelength, but it also works for other general lamps with a general green spectrum, a broader one, for example. And let's say we have this test color of nature, which is some yellow thing. And we measure in Mr. Guild's universe and truth how much, but only with his primaries, photons you should make, and the intensity of the lamps to give the eye the same impression, fool it, with these three primaries as it would have from the real spectrum of the real object. Now, let's say you need 3 green photons and 2 red photons. Now, Mr. Wright didn't originally know about Mr. Guild, but they came together. Now, let's suppose that Mr. Wright chose these 3 primaries. Maybe the green one is the same, and the red one is a little bit more reddish. It has a longer wavelength. And the blue one is a little bit more blue-green. It goes a little bit more towards green than a pure blue. So as I said, we don't have to do all the measurements again. You can simply calculate one from the other, and then we can group it into one unified system. And we can understand color. How does that work? Again, it's additive, so let's simplify it. Let's just imagine that we don't have the red or the blue component for Mr. Guild. And let's also suppose that we have only 1 photon instead of 3, because we can multiply the result by 3 later. Now, 1 photon of green in Mr. Guild's system makes an impression to the viewer. How many photons of Mr. Wright's system do I need to make the same impression? Well, if we assume that it's the same, exactly the same laser, the answer is pretty simple. 1. I need 1 of the green and 0 of the red and the blue to make 1 photon of green. Okay, now let's suppose he didn't know about what Mr. Guild was doing, so let's suppose Mr. Wright chose a green which was a little bit more yellowish, a little bit more towards the red. In that case, I need to make, for example, 0.9 of the green photons, or intensity, watts if you want, and 0.1 of the blue. Why? Because I need to pull my green a little bit towards the position that Mr. Guild had chosen, but I don't have it because I only have these 2 primaries and the third one. So I may need to mix 2 primaries to get the one from the other. Now, the only thing you have to do is measure how these three primaries convert to each other. And that's it. We do the same thing for the red. So we have to measure whether it's exactly 0.2 or maybe 0.15 or whatever. But you have to do that once for the 9 combinations. And let's say for the red one, we need 0.8 red here and 0.2 green. Now, and then it becomes simple, because if we now have 3 photons of green and 2 photons of red to give the same impression to the eye as the yellow piece of painting or whatever it was, then how much do we need of the green primary, for example, of Mr. Wright? And so we know the values that Mr. Guild had measured, and we want to calculate the values that Mr. Wright would measure if he were to redo the experiment, but then you have to call all the people again, please come for daily sessions and so on. No, he can calculate it because we knew how much photons you need to simulate the green of Mr. Guild in the system of Mr. Wright. That was 1 in this example, because it's the same thing, it's 1. And to simulate the red of Mr. Guild, we saw in the previous slide, we saw that we needed a little bit of green to make the other guys red. So we also need a little bit of green to make these red photons that the Mr. Guild had measured in the Mr. Wright system. And these things you can measure once, and these things are the amounts for each different color that Mr. Guilds tell you. So it's simple, it's additive, so it's 3 times the photon here, green to green, and 2 times red to green, and you add them up and you end up with 3.4. You do the same for how much blue do I need in the Mr. Wright system and how much red do I need. Well, if you write that down in a shorthand manner, that's what they call matrixing. And so these recalculation factors, in fact, the values of the primaries in the first system to the second system, they are fixed. You have to just test them. There are 9 fixed numbers. The numbers that Mr. Guild needs as photons to represent any kind of color in the world, whether it's a red tomato or a blue parrot or whatever, these are variable. This is what he's going to tell you. He says, oh, I measured the sun, or I measured ice cream, and I needed 0 blue, 3 green, and 2 reds. And now you want to calculate what the viewers of Mr. Wright would tune as intensities of the lamps of his different system, with a different blue and a different red. And you can calculate that by simply doing these multiplications. So you have the amount of blue times the transfer from Guild to Wright system, plus the amount of green photons times this fixed coefficient, plus the amount of red photons times the other coefficients. And then you have the blue one, and the same you do for the green one, and the same you do for the red one. And so basically you can transform each trio, so each color that Mr. Wright has measured or calculated or camera captured or whatever, and turn it into the values of Mr. Wright. So that's fantastic. You can do this for any secondary trio. So we can define color however we want with 3 numbers. That's great. Otherwise we would have a very difficult story, but now it's still not easy, but easier. So any 3 numbers. So this is called matrixing because people who had mathematics know this is a matrix. And actually if you talk about cameras and they have the matrix inside, then you're thinking of this kind of thing. Now, let's simplify this now for the non-mathematical people in an easier manner. Let's do it geometrically as a shape. So basically all the colors you can make are between a minimum and a maximum, because it has to end somewhere. So let's take the red component. It goes between 0 and between 100. That's the maximum of the lamp of the experiment, or the maximum of my television, or paper white of my printer if you wish. Now actually in 8 bits the number you will actually encounter is 255, but let's call it 100% for now. So I can make colors, any color, let's say an orange color. It will have a lot of red, for example 75%, and a little bit of green, for example 30%, and no blue. And I can do that with all color combinations, and then I get all the possible colors. So a lot of red, little green, they have reds. If you move upwards, you go towards the greens. Here you go towards the perfect greens, because there's no red in the middle of your yellows. If I add my blues, then red and blue gives a purple, also called magenta. If you have green and blue and the red 0, then you get this plane over here. And when green and blue are equal and, for example, maximum, you get the cyan. So you get your blacks where red, green and blue is 0. You get your reds where the red is something, for example, high, and the other two are 0. If red and blue are 0, you have your greens here. Yellow you have when red is equal to green, and also here you have dimmer yellows up to dark black yellows. Magenta is where there's blue and red approximately equal or exactly equal, and no green, so it's anti-green. And you have cyan, which is blue-green, and you have white, where red and green and blue are maximum. You get the whitest, the brightest and whitest possible color, white. And here is our blue, of course, hidden in the back. And you can make tertiary colors, for example, if you mix red and yellow. So for example, 100% red, but not 100% green, but only 50% green, you get an orange, and all the colors inside. So now we have something which we can mathematically represent and also still understand. By the way, it's not the easiest color space for people. People may like circles more, or other shapes may be easier to work with, but at least I guess most people can get an idea of how you can define the colors inside this space. We'll talk about other easier color spaces in other videos. Now it's interesting to turn this on its tip. So we rotate the color and we put it on its black tip, and the diagonal to white we put upwards, because then we have here achromatic or colorless colors, which are the grays. It goes from black and dark grays, ever lighter, up to white. So this is only brightness, and in the other direction we have colorfulness, we have colors. So this is already important to understand, because some people don't understand what happens when they change their camera exposure and suddenly the colors become feeble and weak and desaturated and so on. Already you can understand from this shape a lot of things. So that is actually the limits, both of our mathematics and our camera and our display, so both of physics and the representation itself. But even if you had another representation, the display would have issues like this. So in the tip, what you see are the murky colors, the dark colors. They are pure red here, because here, this was the axis of red, a certain value, and no green and no blue. But because it becomes darker and darker and darker to the eye, it's not a vivid red, it's not a colorful red. And so you have the murky, dark, muddy colors here. If you want to make colorful colors, you should be in the middle of this cube. You should expose, for example, your camera, if you want to capture, for example, colored lamps, neon lights or something like that. If you do it wrong, you will lose all the color. If you do it right, you want it to expose so that the pixels are in this range, because then they're both bright. You go as high as possible, but also colorful. If you go higher, here nothing exists. You have to go all the way back to the desaturated axis of grays and to the whites. So that's what you have here. If you want to make more energy, either you go to impossible colors, or you desaturate, and then you get more light, but you lose a lot of color. So you want to be careful here. In certain instances you want to be here, but often for color photography you want to be here. Another thing I want to introduce, because people talk a lot about color planes instead of. A color plane is a little bit misleading, because as I said, actually you have a color solid, a color shape, 3D. Because the color plane suggests that you can make all the colors inside for each and every intensity or brightness, and you can't. You can make all the colors inside here in the bottom part, but you cannot make them here because all of this doesn't exist. If you go very bright, you can suddenly only make the center point of the triangle, namely the bright. But in any case, the color plane can be made by connecting the three maximum points here. Maximum red, 100%, blue and green. And then you have the maximum amount of colors you can make. You can't go further, but everything should be in there. But as I said, sometimes you can't even make bright red when it's very intense. But this is a representation people also like to use, the color plane. And it is generated like this from the color solid by connecting the three vectors of the maximum red, green and blue. And then you pretend there's no brightness, there's just categories of colors, reds, yellows, greens, cyans, blues, purples, etc. It's a little bit simpler shape. So, returning to the different system of Mr. Guild and Mr. Wright, let's see how it works. So, let's say Mr. Guild chose a very good green primary, and Mr. Wright chose a rather yellowish green one, and Mr. Guild chose a very deep red primary, and Mr. Wright chose a somewhat orangish primary. Then we can take these triangles, and we see that the triangle of Mr. Wright, because he chose bad primaries, is much smaller. So now it's important to understand, you have to believe me for that, I can explain it in detail, but then the video would become long and boring. You can only make colors inside a triangle. So the people working in Mr. Wright's system cannot make these colors of Mr. Guild with the lamps. That doesn't work. That's a problem. At least not physically. Mathematically you can make these colors by negative numbers. We will see that later. So ideally we need very good primaries which all have positive values to make everything inside. Actually this three-dimensional representation is just a projection of a, for those who care, of a 27-dimensional space. And actually that's why metamerism works, because you can have a certain color for the eye, but there can be many other dimensions, and all these spectrums will give exactly the same color. But okay, that's for the specialists. Please forget it. The professor sometimes wants to be a professor. So I talked about the possibility of making certain colors and not making other colors. This is what Mr. Guild and Wright saw, because they asked their experiment people who did the experiment, please mix it and then give me the numbers, and they did so, and they said, we have a yellow thing, okay, then I mix a little bit more of green in the red, very good, very good. And then suddenly they got, for example, a cyan color, and they started mixing, and I can't get it, I can't, there's no way to mix more red or less green, you're doing such a bad job, blah, 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 blah. So a little bit of panic. But then they realized this problem of the negative values. And they said, well, if I need to make, for example, for the cyan color, minus 10 photons or intensity of the red, which is impossible. I can't, like a black hole, suck the light out of the system. But of course I can put it on the other side. It's just a trick. Mathematics always works. And then instead of putting minus 10 here, let's put plus 10 red there. And then actually I don't mix the cyan color, but I mix, for example, a green color or a yellow color or whatever that I can mix. And I can still define the system now, as I can mix these two to give the same color as these three. And then I can say each time I mix something on the right side, I will pretend it's a negative value on the left side. Hey! Now suddenly they could mix everything nature could throw at them. So actually nowadays we can understand what was going on. These were the primary colors that Mr. Guild and Wright chose. Together their common system. Because they were convenient at the time. They should have chosen maybe this and this and this, because then we would have had a triangle which almost covers everything. You can't cover everything quite because there's this rather curved part here, but anyway. And yeah, as I said, they only can make the things which are inside the triangle with positive amounts of light, and everything outside would have been the negative mathematical value, but they could cover that because they could put the light on the other side, and each time somebody said, oh no, I have to control the light on the wrong side, then it was a negative value. So no problem, they could define all the colors, and basically this horseshoe shape is all the colors that humans can see. Everything that exists, there's nothing outside. And they could define all of these, and these would have negative numbers. No problem. Actually, nowadays, this is an example of a practical primary system, so-called REC 2020, which is used in, for example, the modern, very colorful televisions. The old televisions used to have a much smaller triangle, but here it's still not perfect. You can't make everything, but these greens are so saturated that you almost don't see them in practice. Most colors you encounter in nature fall within this triangle anyway. So with these very colorful modern TVs, you can make almost everything which exists in nature, and more importantly, beautiful colors. That's called REC 2020. But Guild and Wright said, let's make yet another even bigger triangle which encompasses everything. And they call that the XYZ triangle, and you will encounter it often. It's the so-called standard human observer. Everybody sees color slightly differently, but on average we see color more or less the same, and you can define what we see by these XYZ values. And in fact, since the triangle covers everything, the X, Y and Z value will all be positive. That's nice. But there is of course a problem. I said over here, you can't have your cake and eat it. Over here, the colors don't exist. So these primaries, you can make them mathematically, you can define them, but you can't make them as lamps. So that was good for Guild and Wright, because they were working at the time before the computers in the 1930s. They still had to do all the calculations with the slide rule and what have you. Modern people don't even know what that is. But And they said, well, let's then not have negative numbers because it's way too complicated and confusing, and let's define this. But in practice nowadays with our computers, even inside the camera, you can do millions of calculations in a chip, no problemo. So actually we can just as well use the Rec 2020 system to define all our colors. And since these colors don't occur often anyway, most colors will even in practice be all positive within Rec 2020. But even if you do encounter this, well, then you have a few negative numbers. But this XYZ system is the basic universal color space. So actually, what does that mean? If you look, you will encounter a mind-baffling amount of color spaces. Why are there so many? Because, yeah, the brain and the eye is quite non-linear, and the world. So actually you would have a space like this, but that's complicated. People would like to use a sphere or maybe a cylinder or a cube or a triangle or something. That's easier to understand what's going on. But the world isn't a triangle. It's like if you approximate North America by a triangle. It's quite reasonable in most situations. But here in Mexico, because the Gulf of Mexico, you have to bump it all back out, they would make a lot of error. So either you have a complicated space, or you bump it up, stretch it and pretend it's simple, but then you make colors anyway. So that's the way it is. So that's why people said, well, let's make different color spaces for different uses, for different things we want to do with it. And I'll detail some of these color spaces in other videos so that you can better understand it. For now, let's forget again about all of this. Let's say that we do everything in XYZ space. And then, again, you can make any color as a triplet of 3 components. So much X, so much Y, so much Z, and then you get a position somewhere. Now we need one more concept, and then we're good to go to understand how a camera works. And that's color matching functions or sensitivity functions for the spectral wavelengths or elementary colors. Now we said that Guild and Wright were measuring on the right hand side of their test field. They were measuring all these elementary colors, all these different wavelengths, yellow up to red. And they were testing how much intensity or photons counts, if you want, for each of these situations you needed. So for example, for the blue test color, you need 100% blue and no green and no red. And here for the yellow you need, as we said, 20 and 80 and 100% for the red color. But that's a lot of numbers. It's difficult again to get your head around it. So why not write them as curves? And then we see, the more we move to the red, then our need for the blue lamp, so the intensity we need to give it, goes down to 0. And the red intensity goes up, the more red we need to make, and the green goes kind of like this. And now we have something we can understand. If we have to make greens in the middle, we need a lot of green lamp. And if we need to make reds, we need a lot of red and no green and no blue. These curves we can understand. And these are the color matching functions. The amount of a certain primary color, each of those 3, we need to match any spectral sensitivity. That's basic information to define each elementary color. And as we said, it's additive. If we know how to make 1 unit of this elementary wavelength, and if we know how to make 1 unit of this yellow wavelength, then we also know how to make 5 times of this and 3 times of this, because we just have to add 5 times this and 3 times this. 5 times the blue needed for this one, and the blue needed for this one, which is 0 in this example. And the green we need is 5 times this one, which is 0, and the yellow is 3 times the amount of sensitivity we have here. So in general we take the sum of the heights of all these bars, depending on what shape the spectrum has. So let's say a U shape or something. And the sensitivity for each of these positions, for each of the 3 colors. And then we have the total amount of blue we need, the total amount of green, and the total amount of red for any kind of spectrum shape, also for this S shape or whatever you want. So it's a little bit of calculation, but now we can do whatever we like. Actually, you can in this way also define the sensitivities or color matching functions for the XYZ system, which is the standard human observer. So if I need to know what my XYZ value for this yellow color would be, I just read the height here for 1 unit, and then I multiply it by 10 if I have 10 units here of yellow. So the Y value will be on the green, the X value will be on the red, it will be slightly lower, and the blue value will be 0 because yellow is anti-blue. That's how it is. And we can do that for any other elementary color position. And then we can again add them all together. If we have a certain spectrum, I add the blue needed for this position, and blue needed for this position, the blue needed for this position, and blue needed for the amount of energy I have in this position, and the amount of energy I have in this position. And I do the same for the green and the same for the red. And these give me the total X, the total Y, and the total Z. So that's how you define what an eye would see. It's not actually the cones of the eye. Well, the blue one is an approximation of what the sensitivity to all the different wavelengths is of our blue cone. So how strong it fires to the brain. But the green one is not. Again, it's the 1930s. There was not color television even in those days. People were doing it for illumination. And so they just wanted to know a brightness function though. So they said we'll make this shape a little bit different. Again, we can matrix it, and then we can change shapes. And indeed the brightness you see with your eye is a combination of how much your red, green and blue cones are activated. And then the brain says, well, they're activated, this one is, and the red is activated so much, and the green so much, and the blue so much. So it's probably this bright. And the brightness of each and every color follows from this function. So we see that our eye is sensitive for green yellowish colors, and it becomes less and less sensitive the deeper the red becomes, and it's also very unsensitive for blue colors. And so you need to pump a lot of energy in blue to make the eye see it bright. And the red one is actually a mixture where we had a lot of blue in there, so there's a fantastic second bump here, which is also not necessarily how the cone works, but it doesn't matter. This is how people say the standard observer works, because you can calculate it in cones anyway if you wish. That's our basic thing. So we could build a camera with exactly these curves, and then the camera would see exactly as the human eye would see. End of story, no more complexity were there. However, again, that's not how they do it. And that has consequences also for how you shoot your photos. In fact, we don't need to know what exactly the eye sees. We only need to define which colors we need to display. And because the camera has to measure how much my television or monitor, how much red it should display, not how much red I'm going to see. Because I will see it anyway if it's correctly displayed. So we want the camera to measure immediately the amount red of green and blue needed. But that it depends on which red and green and blue. For example, the display we had in the previous century, many of you will remember it, it was the heavy bulky one, which was as deep as it was wide, was called the cathode ray tube, CRT. And this did has phosphors on its front screen, and the phosphors had the spectral energy distributions that you have here. And so a lot of spikes in the red, and the green one emitted this kind of light with a lot of green and a little bit less here and a little bit less here, and this was the blue one. But of course, a liquid crystal display, the flat displays that you have, will have totally different light emission spectra, so they will have totally different primaries, so they will have a totally different behavior and a different red, and I have to mix more red or less red than in case of the CRT. But the CRT became the basis of the colors which we have now. If you do a JPEG photo or whatever, we always assume that basically, unless we say differently, it's called SRGB, standardized RGB, and they are defined based on this CRT. Now, how does it work? Again, bear with me, it's not that difficult. I will take any color, it can be any spectrum, but let's say again an elementary wavelength of a yellow laser, and I will put it into our eye, and we said these three curves are the standard eye, so we can approximate as if it were the spectral sensitivities, the sensitivities to different wavelengths for a standard amount of energy of that wavelength of the three cones, the blue cone, the green cone and the red cone. And we can calculate what comes out as total sensed signal or color component. So if it's just a single wavelength, it's easy again. The X color will become the height of this curve, so it will be here approximately 1, and the Y of the color will be the height of the green curve, again for this wavelength 600, whatever it is, and that will be, for example, 0.8, and the blue height will be, the Z will be 0. So I know this color is uniquely represented by 1, 0.80, and any other color spectrum, whatever you want to choose, has these numbers. And now I want to find out, and my camera should do that automatically, how much of the CRT pixels should I irradiate, so how much light should each pixel in a certain position give of the red, green and blue to have exactly the same impression to the eye. So my X color here will now be a combination of how I shoot these three amounts of light. So the red, if I put it with an elementary intensity, let's say 1 watt or whatever, or 10 photons or whatever, then I see that these photons come in here in the curve and they are sensed here and here and here with a certain sensitivity, and that one amount of red will give a certain amount of X, namely the sum of these bombardments and the sensitivity to that photon bombardment. That will be a value. Again, I have to calculate or measure this only once, because one amount of red will be defined stable, and this curve is also known, it's the standard human observer curve. So this is a fixed number. And my green will also give a certain amount of activation of the red, because the red goes a long way up to the blue here, the X curve, and the green also goes all around the place. So the sensitivity of all these positions, sum them together, will give the amount of X coming from switching on the green pixel of a CRT, and the same with the blue. And now we want to know the variable numbers, red, green and blue. Let's say I need to put this at 20 photons and this has 8 photons and this has 4 photons. And I need to calculate these variable numbers so that I get exactly the same value as my test value. And the same for Y and the same for Z. Now, for those who know a little bit about mathematics, the others don't care, we'll come to what it means later, just believe it. With all these values here being fixed, and only these 3 red, green and blue values being the variables we want to calculate, and these x, y and z is also known because it's the color we need to make. I can solve these three equations and I can do the values R, G and B. It's high school mathematics. And that's actually what the camera does. So then the point is, what do I know then? Then I know exactly the amounts of energy I need to put in this CRT display with these primary behavior, these light emission spectra, to produce, to fool the eye as if I was making this yellow laser or maybe a yellow lemon with a different spectrum. Fantastic. Now I know exactly which values I need in each and every case. And if I convert these values for all the spectral colors, so the red, green and blue I need, if I calculate this for all the, let's say, 50 spectral colors, I get again functions. And they look like this. And that's what the camera should output. So if the camera senses, let's say, our green laser, it should output, or our yellow laser, sorry, or a green laser or whatever, it should output this amount of green, which is 1.2, this amount of red, which is in this example 0, for example, and this amount of blue. But wait a minute, we have a problem again. It's mathematics, we end up with negative numbers. Now you can't make a display which makes negative light, which emits negative light, but you also can't make a camera which makes negative light, because I can try to make such a filter by chemistry, and I put it on top of my pixel, and the pixel does nothing but count the photons coming in, and the filter says how much of the photons come through. So a normal pixel without a filter would be equally sensitive to everything, let's say, and I make it more sensitive by having a filter which transmits more, and less sensitive by having a filter which transmits less. So I could, in theory, make this. Quite difficult to make it in practice, such an accurate shape anyway, but I could in theory make it. But I cannot make a filter shape which gets negative photons in the pixels, which kind of sucks the photons back out. That doesn't work. I could of course make a filter which makes such a positive lobe and then subtract it in mathematics. But then that's still difficult, because we like to have high resolution sensors with only one red, one green and blue pixel. And now I would need, for example, 3 pixels already for the red. One which measures this, one which measures this, and one which measures this. So that's what we need to make the camera behave exactly as the eye, to give exactly the right colors, but it's not useful. It's not easy to make. We could say, well, let's make the positive shapes then and ignore all the negative things. Let's just put it to 0. But then you make quite big color errors, because here you would need to remove some of the red. And if you don't do that, you have too much red for all colors that lie here. So a color that would be cyan, you would move it towards the red, which is anti-cyan, so you would desaturate it. Again, not so good. What happens actually if you do the color measurements, for example here, in case you get a color like this, which is deep red, it gets seen by the camera as a color like this. And as I said, for example, green can get desaturated towards the whites. So, not a good camera. How do we solve that? Well, you could again use matrixing. So, what I did here is take in dashed are the actual curves of one popular camera on the market. It actually has these curves. So you see they're not like the human eye at all. For example, in the red, it goes down much faster. So here, for these yellows, where the eye would still generate a lot of red component, the camera already generates nothing. So it will not have enough red in its final color. So again, the colors will be wrong. What you could do is matrixing, and then you try to match with whatever function you have to match it as close as possible. So now you see that here also the green was not actually measuring green in this camera, but it was more measuring blue-green instead of green. So with the matrixing I move it all the way up to the other curve, but yeah, it's still not perfect. You get more errors here. So actually that's also not the way to do it, because it puts too much emphasis on elementary wavelengths, which you don't see in nature anyway. So actually the only way you can have a matrixing, a linear combination of functions which will exactly be the ones you need for the human eye, will be if the original functions already were a linear combination, deformation. And they aren't, because they're whatever the camera maker, for whatever reason, cost of production, availability and so on, has made. So how do we do it then? Well, let's first see how can we measure, what's the problem with color errors, how severe is it? And for that you can use a set of test colors. The most well-known one are the Macbeth colors, and they actually contain a patch of so-called Caucasian skin, which most people would call white man skin or white skin, but I've never seen anybody with a white skin. There is dark skin. It's again, you have of course all colors of skins, but this is kind of an average of, well, what the guys of Macbeth thought would be a good representation of dark skin. Then you have, and it can be quite difficult also, indeed, to have the correct color for skins, and people are very critical at it. So you have sky, that's also typical object foliage, and they have typical colors all the way spread around the color horseshoe or triangle if you wish. Some reds and yellows and magenta and cyans, and some yellow greens and so on. Now, what I've shown on the left is the actual color as it should be, good skin, and here you see the purplish skin that this camera would give if you just capture the color and didn't do all kind of magic tricks, calculate inside the color. Now you get the blue shift, as we saw, the blue of this camera was not very good, so you get kind of like, it's not very good, it's not the same, at least, let's say it like that. And as we see, indeed, a lot of colors get desaturated. It's particularly bad with the yellow here. Instead of a vivid lemon yellow, we get this post-it yellow. And the same with the magenta. So probably you wouldn't sell this camera. By the way, the ones that don't show a difference, it doesn't mean that there is no difference, but I didn't want to do so many more simulations, calculations, so these will do more or less the same thing as here. Now, what can we do then? We can matrix the colors themselves. So let's say we have a set of colors here, the blue ones, and white is in the middle, and the colors get more colorful the more they go outwards. Well, I can transform all these colors all together by doing the matrixing again, mixing in some negative values. Maybe I can do that. Because matrixing is a powerful technique which can be used either to change basis systems, but also to change the color inside the fixed basis system. Very useful also if you want to do color processing. Let's look at the real image, what matrixing does with real photo processing software. So you have your greens and your blues here. Let's use the channel mixer. It has here again an amount going, well, even above 100%, and it can go negative. So let's mix in the blue channel. So if you're gonna add in more energy, things are gonna get more blue, because this is the output channel. Now, the normal situation would be there is no blue original color and no green original color, input color, in the output. If you don't do anything, blue is just blue. It's 100% blue. But now I'm going to transform that pixel trio color definition by adding more blue depending on how much red there was originally in the picture. Or I can, for example, do the same with the red component of the output pixel color and the result. And I can do, for example, make it more red depending on how much green there is. And you see that here, for example, the green trees get more red energy, so they move towards the yellow and the brownish, a little bit autumn-like, because this green component stays the same, but the red component is increased. You see it also here in the clouds. It doesn't do much for the absolute white, but you see here that a lot of red is added to the original color, because in the white is also some green component. And so it can go all over the place. You have to use it with care and maybe with a mask. But the point is clear. If your camera, for example, makes these rather dull green colors, you can do the numbers the other way around, negatively, and make it more greenish. So that's what I actually did, and it works like incredibly well. So now here we had our original color again. Here we had the wrong uncorrected color of the camera. And here we have what the matrixing would create as best approximation of the color. So what you would get in your JPEG output, where the camera all does its optimal approximation. You see, well, for all these colors, especially the faces, I didn't do anything specific for the faces. You could do something non-linear where you give a lot of focus on the face colors because they're important. No, I just used one optimal matrix, which I calculated, and it's almost perfect. You almost don't see any difference. And for a lot of other colors, it's also quite good. Now, sometimes you do see a little bit of difference. It depends on how critical you are. So here, for example, for the blues, it's still not perfect, but it's incredibly good. So now suddenly we have turned, with all these problems, a camera which was quite bad, with the filters that it had, for whatever reason, we turned it in a quite satisfactory camera, because again, you can debate about how critical you are. This blue is not exactly this blue, but if you didn't have the original color in the first place and you would get this as the result, you would be quite satisfactory. Whereas if this becomes your face color, you would maybe hand the camera back in and buy another one. So, it's very good. So, but wait a minute, I optimized on a set of colors. What about other colors? And maybe it goes well for the ones that I used, but maybe other colors go wrong. Yes and no. Now it becomes interesting. Of course, if it's all continuous and smooth, and you get an orange color which is not so far off from the oranges that you already optimized on, because there were orange colors here, then, well, this is an actual. So here I took the fruit, an orange, with a spectrometer. I measured the spectrum with the spectrometer. I did all the calculations of how it would be seen by the camera and so on and so forth. And we see that, again, it desaturates with the uncorrected camera, but with the mathematically optimized camera inside of the chip of the camera for the JPEG that comes out. It's almost perfect. A plastic bag, it's not that perfect. So you see, it all depends on where the colors are. It doesn't go perfect for all colors. It kind of goes all over the place. But at least this color is closer than the uncorrected one. Here, it's probably also a better color. You would still accept it. The blue ink of a ballpoint, it's not exactly as it came out, but yeah, you would accept that this is also blue ink. So there are some errors, but it's acceptable. Except for some colors which go really bad, and these are, so here these are smooth colors, like the color, the spectrum of an orange goes kind of like this, like an S, smooth S, and the light of the sun also goes like this, and then it behaves well. But you have also lamps, also some objects, but mostly the lamps that illuminate normal objects, which contain atoms like mercury atoms, and they produce spikes. So some of these lamps are, for example, the long TL light you can have in your bathroom or something. LEDs used to be a problem, a little bit less nowadays, but also the lamps that you have on the highway and in the street. And because of these spikes, it's very difficult to predict where the spike will fall on a curve and whether it will move to where the sensitivity of a camera is high or low. It will go quickly different, and it's very difficult to. And so what could happen here, for example, with this kind of lamp, kind of face-like color, it becomes very pale if I don't use the correction. But if I do use the correction, it seems to go in the wrong direction. It seems to over-correct. And you get green faces, and that's even worse. And that's known by photographers. Also here, you get a totally different color. So that is a little bit of a problem, which cannot be solved by simple estimation or optimization. We have to live with that. But now we understand it. It's what we see, for example, the green lamps. If you see it as human, it's not that green. And everything around it, also the tiles of the street, they become this dirty green. Or maybe if you were not to correct it, and then you can say, oh, I'm gonna shoot RAW, I'm gonna do it all myself. Good luck. Well, anyway, can we correct it? Even if we shoot like probably most, at least amateurs, if we shoot in JPEG, can we still correct it? Well, yes, we can do something. So one thing we could do in software is the so-called white balance. So I tell the software the tiles are not supposed to be green, they're supposed to be gray. And then it goes okay. And many other colors also already. And the car here, you now finally see that it's a blue car instead of a greenish blue, greenish ugly car. So that works already quite nice. However, the lamp itself is still this strange. So what you could also do is mix in the total picture some anti-green, which is magenta. And then the road becomes a little bit magenta. It's not too bad. It's acceptable. And the lamp becomes, a better value. And you could, of course, do a blend between these two, depending on where you have it. You could try to do more complicated color grading, but the problem is here that you have all kind of different lights, also in the background, that may not be illuminated by these lamps, but maybe by something else. And then you have here the blue of some shop window or something, whatever. Yeah, and all of this gets thrown in the direction of magenta also. So yeah, that may be a problem. So this goes too far and then it becomes too magenta. But you can get more or less. You can do it as pre-compensation or post-compensation. What do you do in pre-compensation? You just put a filter in front of your lens, which cuts out the green spike. And then it does the same as we did in software. But the problem is, as I said, it will also remove green that is supposed to be green, a green car. And what about these spikes? It will also remove them, or not remove them. And so, yeah, maybe you better do it. It doesn't work so much better with a filter. The filter only works on average approximately, which you screw on the front of your lens. So, in conclusion, why don't we make a fully accurate color camera with exactly the human eye sensitivity curves over the pixels filters? Well, first of all, which customer actually cares about exact precise color instead of a beautiful color? Yeah, sometimes you want to measure some color exactly as you saw it, but most of the time you just want reasonable colors. Except if you have scientific work, maybe. It's also difficult to make very precise filter shapes, so your camera would cost a lot more than it does now. And we saw, if you just take shapes that you can make, well, and optimize then on the pixel sensitivity itself and the amount of pixels in a chip and the size of the chip and so on, then you still get decent colors. Besides, if you optimize the sensor, then what if you change the lens? It starts behaving differently. Do you want to do something special with all the different lenses too? Becomes complex again. And the measurement would be correct for some light and object combination. But actually we want to measure the object colors perfectly, not whatever light you had. So you have this difficulty with very difficult lights, like the spiked street lights and so on. That's gonna be a problem anyway. And last but not least, photographers like to change the color anyway. So the camera, if it were to make fantastic perfect colors, then half of the photographers would say, yeah, but I would like the red. If it had been more red, okay, I gave the guy the wrong shirt, but I'm gonna correct it. And the color processing also introduces very interesting complex shifts in color, which we will talk about in another video. So actually people just talk about the dominant color aspects, and you can change these in your camera settings. So if you have these two, you're already good. One direction, you make the color more vivid and more saturated, or more plain and more desaturated. That is going towards white from every color direction. And the other one is so-called the color of the white point. Because the light can be a little bit more bluish, or it can be a little bit more yellowish. And this is, if you have sunlight, everything will look a little bit more yellow. And in the shadow, it will look a little bit more blue. So if you set your color balance the other way, you can get for the same situation a compensation. So instead of yellow, it gets in the other direction. So you indeed see this can come out of the camera depending on whether you desire it or not. And if you don't desire it, you can make this blue image a little bit more yellowish again in photo software. So these are the two dimensions that most people care about, and that's what they say when they talk about color being correct or erroneous. Some people will like a bluer image, comes out of camera. Some people say, no, my camera images are always too bluish. I will like them a little bit more yellowish, but then either change the settings on your camera or do it in photo software. And if you correct these things, you already come a long way. Again, as we saw, this yellow patch, if it was a very special yellow, it would maybe be a little bit wrong, but it will always be a yellow. And the dominant changes whether it is too bluish or too desaturated. And that is something you can relatively easy do. The rest is highly difficult, as we have seen with the example of the street light. So then some people say, can't I solve it by profiles, the magic thing, make a camera profile. But again, the profile won't solve the conversion of a spectrum to the red, green and blue pixel measurements the camera actually does. Once this is done, if it's wrong, it's wrong. What you can do with the profile is, of course, if your camera gives on average something which is too blue, you can make it a little bit more yellow in your color management profile. So no, you can't correct for how the camera behaves. There will always be some color errors. End of story. Unless you change them pixel by pixel in the software, so to speak. Worst case, of course. So the conclusions. No photo camera on Earth will accurately measure the actual real-world colors, that is, as the eye does, because the real world is a 2 × 31 dimensional thing, where you have a very complicated light spectrum and a very complicated object spectrum, and we summarize it in 3 values, and that can't go perfect, especially not if you have just whatever filters in your color pixels in your cameras. So it's kind of pre-shuffled. You get out of the camera what you get. Most colors will be reasonable. Some colors can be quite wrong, depending on how critical you are. And the colors can go all over the place. So it's not just dependent on if you have a color which is, for example, in the green area, because it's a green object, then you would say everything would go the same. But then you take a slightly different green object. If the first green object goes more towards green, the other one could go in the opposite direction. Or even you take the same object color, which is an object color under standard sunlight, and then you change the lamp and suddenly it goes again in another direction. So everywhere in the color triangle it can jump into all kind of directions. But most of the time it goes well, and sometimes it goes weird, like with these green faces of streetlight. Then again, color accuracy is not a real problem for many photographers. They don't even think about it unless you follow these courses. And we tweak the colors anyway. But of course it's better if the colors are already correct, because tweaking costs a lot of time of the photographer. You don't want to spend 10 hours on each photo you make. And I also didn't say that color is not important. Sometimes it doesn't matter. Nobody knew which kind of shirt you wore and whether it was slightly more red or less. But of course, if you have a logo or a trademark, Coca-Cola or whatever, it has a certain color maybe. And that you should do as good as possible. So color is important, especially for some professionals. Anyway, the camera will do its best to ensure that the colors are close enough, apart from, as we saw, some problematic light, and try to avoid it. Try to use decent lamps, decent stuff. We'll talk about that in other videos. And as we said, we can usually ignore all the difficulty of spectra, except, next slide, we can usually ignore that and just talk about the primary color aspects in these 3 dimensions. So it's a little bit too blue in the blue direction, or a little bit too red, and so on. And if we correct already for that, for example a white point shift, we will learn about that, then you're good to go in almost 100% of the cases, not 99%. However, why did we teach all of this? You have to understand the shape of the spectra to bring out the own color of an object. So these mushrooms, for example, they have a lot of yellow. The spectrum here goes over red and a little bit yellow and green, and then no blue. So I want to use a spectrum of light that also has this shape, more or less, preferably. Because then what happens if I multiply these two, then I get 1 times 1 for all these wavelengths. But here I get 0.1 times 0.2 is almost nothing. So instead of a little bit of blue still in the resulting spectrum, like if we have here, if we illuminate the object spectrum under perfectly uniform lamp, which has the same amount of blue light in it as red light, then you keep the same spectrum, and then you have the difference between yellow and blue is 10 to 1. This is still 10% of blue, which desaturates the yellow. It makes paler and less beautiful yellows. And here you have almost perfect yellow, which is anti-blue because you have removed the blue. And now you see these beautiful yellow mushrooms. So you see here the color is pale and has moved much more toward the axis of colorless grays, and here it has moved much more towards most saturated color. Of course, it's still a natural color, it's not these flashy cartoon colors. Aha! And that's the trick. For example, your butcher may use red lamps to make the meat look more tasty, or the lobster or whatever he puts there. Aha! And maybe lobster is already red enough, but the meat. That's the trick. Know the spectrum to bring out the properties of the object by having similar light. That's the advanced story. Indeed, if you see, the green here kind of blends in the totality and is less conspicuous, whereas here it becomes almost predominant. It's a totally different rendering. And maybe not so easy to do. Well, you can also do a lot of stuff in processing, of course. But now we did it automatically with the lamp. So, long course, but I hope you learned a lot. about what cameras can and cannot do, about what goes wrong when you have the wrong light, or what goes right when you have the right light, about understanding proportions of yellow, red and blue and everything, and what it gives in the final 3-component red, green and blue color. In case you want to learn more, please subscribe and follow some of my other videos on other topics. Bye guys.